Okay, great. Let's try. So today's lecture and the next lecture we are going to have will basically construct expanders from scratch. So in today's lecture, I'll already give you some examples of expanders, which for almost all applications, these are already good enough, in the sense that they are going to be super explicit and so on. But proving that they're expanders is going to be non-trivial, and we will not be doing the proof of those. But then we'll come up with a different constructions where we can prove everything from scratch. Okay. So just a brief recap. So we were looking at this, we were basically using this notion of spectral norm to have a sense of expansion. So spectral norm for any operator M is just defined to be like the norm of Mx in relation to the norm of X. Okay, and you want to know what is the largest that this can be amongst all possible non-zero vectors that you may have. And as far as expansion, etc. is concerned, lambda g is basically like spectral norm once you ignore the component along the all ones direction. Because you only consider the spectral norm with restricted to the component orthogonal to all ones. And then you ask what is the norm of that. And we saw that because this matrix M, the random walk matrix, had a nice set of eigenvectors and so on, this really just amounted to between the two extreme eigenvalues you could have, lambda 2 being the second largest and lambda n being the smallest. Not an absolute value, but I mean like actual eigenvalues. You just ask amongst these two, which is the largest. Okay. So that's what this lambda g is called. Sometimes lambda g is also called the spectral radius, because if you look at a ball around the origin of this much length, somehow all the eigenvalues are contained here, except of course the all ones. Okay. And something that we saw last time was this very useful matrix decomposition, which gave something like an if and only if guarantee about random walk being an expander. And which was that, you can always write your matrix, if you know it is an expander, the following two are equivalent. That is, if you write M as gamma times this independent random walk, by which what we mean is it's a matrix where every row was just a stationary distribution. Okay. If you're thinking of deregular graphs, this is just a matrix that's made up of every entry is 1 by n. Okay. And if you subtract M from this, whatever is this residual thing, this 1 minus gamma, like if you think of that as 1 minus gamma times E, so it turns, this should have been less than E. Okay. We want to sort of say that the error term, once you remove the independent part, is small. And this gives an if and only if characterization of whether or not your random walk has the expansion property that we want. So this is something that we saw. And we saw an application of this to prove the hitting property of expanders, which was that, if you have a set of vertices B, which you're going to think of as some bad set, and let's say the volume of this bad set is mu, and again, this volume must be defined appropriately. If you're working in a deregular graph, then this is just a fractional size of B. But if you're working in a different graph, then it's the size when you sample according to the stationary distribution. Okay, but from now on, we'll mostly be dealing with deregular graphs, so it might just be convenient to think of that. And we saw last time that if you take a random walk, basically you choose vertex V1 at random, and from that point onwards, you just keep choosing random neighbors one at a time. We saw that the chance that all of these T vertices are within the set B is roughly like mu to the T. And what do I mean by roughly mu to the T? Well, of course, the first one is completely like it was a uniform thing. So there is a factor of mu that shows up. But everything else, you would have ideally liked this to be mu power T minus 1. But this says that this is a little larger than mu. So it's some convex combination of mu and 1. And how small lambda is sort of telling you, is that closer to mu or is that closer to 1? Okay, and it sort of exponentially decays with respect to that parameter. Most of the time, what people do is they just ignore this and write T here. They just put the first mu also as this. Sometimes it's just algebraically it's easier to work with this or something. But intuitively, the takeaway from this is that once you know that your graph has a certain spectral expansion, you know that this is some quantity that is between 0 and 1, and therefore it decays exponentially with respect to the number of steps in the random walk. That should be the takeaway. Okay. And the same thing can be extended even to the Chernoff-like property. Previously, we were asking, what is the chance that your random walk completely stays inside? But you might want to say that, if I take a random walk of t steps and if B is a set of density mu, I should expect mu fraction of these vertices to be inside. So I would like to say that the fraction of vertices that stay inside this set, it should be like the expected value. Okay, and the most general form is that you just define some particular function, okay, on vertices from 0 to 1, some bounded function that you have, and then you ask, if I did the empirical average of this function by taking a random walk versus the true average, how much do I deviate? And this says that, the deviation by, this should have been lambda. So the deviation of more than lambda plus epsilon is like, it again goes inverse exponentially with respect to the error term is very similar to what you get in the Chernoff. So it sort of says that, okay, the initial deviation, I can't quite guarantee much. Like there is an interval of lambda that I can't quite say that you will be within that, but anything beyond that, it starts decaying like you expect it to decay in the Chernoff.
So explanation of RGC was like lambda was in the exponent instead.
So there is also a different version where you replace this with epsilon and then you put an extra lambda there or something. So there are different versions, but many times, because hopefully by the end of today's lecture or something, if you want to get an accuracy of epsilon, ideally I would like to set my lambda to be epsilon also. So that I will basically say this is like a 2 epsilon deviation and I can handle it. So then it sort of puts us back in the regime of the usual Chernoff bound. Some constant here changes, but no, we're going to ignore those constants.
So it's an omega lambda, right?
So yeah, if this lambda was not there, that would have been an omega lambda. Yeah. Good. Okay. And so since we saw this and we were using this for error reduction in BPP algorithms and so on, trying to reduce the error by not being too wasteful in the amount of randomness that's used. Something that came up there was, well, okay, fine. Like in order to do this, you might want to choose a lambda of your choice. You have a certain lambda that you're interested in. And obviously, in order to get better and better lambda, there's obviously going to be some sort of trade-off between the lambda you want to achieve and what the degree of the underlying graph is. Because if you recall all these random walks, at every point you need to choose a neighbor, and that's going to take log d steps, log d random bits. So you need to have some sense of, how is log d in relation to lambda. Okay. So, so the question we can ask is, if what you're allowed to use was a deregular graph, how small can you make lambda? Okay, I tell myself that I can't work with more than 10 regular graphs. What's the best I can hope for that? Okay, and Alon and Bopanna, they showed that if you have a deregular graph, and in fact, this is a statement about deregular graph families. That is, they're thinking of a family of graphs of growing number of vertices, all of which happen to be deregular. And they want to know what is the asymptotic behavior of lambda as you go in the family. And Alon Bopanna basically says the asymptotic behaviors will be at least as large as something like 2 over square root d, if you ignore all of these other terms. So the formal result is, there is actually a 2 square root d minus 1 by d minus some quantity, which will have something like n in the denominator. So like if n becomes larger and larger, that quantity becomes closer to 0. But for some constant sized things, you might get something that is better than 2 square root d minus 1 over square root d. But you don't have a family of graphs that's going to be better than this. So this says that this is a lower bound on what your lambda can be. If you're thinking of a family of graphs and asking what's the best lambda I can hope for, well, your lambda has to be at least this large. You can't get smaller than that. Okay, is that okay? So this was Alon Bopanna's result. And you had a question or something? Okay. And
this result is from
it's probably what, early 90s? Yeah. It's actually a very short, very slick paper. Yeah. So, and graphs that happen to achieve this, up to some constants that some small changes that are there, are now called Ramanujan graphs. And there is a curious history behind this. So the first family of graphs that achieved this was actually constructed by Lubotsky, Phillips, and Sarnak. I will mention it a little later in today's lecture. And the paper was titled, I think, Explicit Expander Constructions and Ramanujan Conjectures. So in order to prove that the graph was an expander, they use a certain proof method, which is also somehow relevant to some Ramanujan conjectures. And they called these graphs as Ramanujan graphs. And nowadays we call those graphs as LPS graphs because it was made by Lubotsky, Phillips, and Sarnak. And we say that, in general, any graph family that sort of achieves this Alon-Bogana bound is now called Ramanujan.
So Ramanujan conjectures were probably not.
They were number theoretic conjectures. They were number theoretic conjectures. And
in terms of graph.
yeah, and it's just that LPS also required studying certain kinds of groups, and which had relevance to those conjectures, and hence the name.
Anyway, I thought in the Ramanujan graph definition, the class model one term is not allowed. For example, we know that probabilistic method does not give Ramanujan graphs, but if it gives graphs for lambda is with plus model.
Oh, okay. Maybe this plus one term is not there.
In the extended graph, starting says that you are
Oh.
not this plus model of one term.
Whatever.
This Pitman says random graphs. Satisfy this with plus
This,
model.
yeah, random. If you pick up a random deregular graph, it turns out that the lambda that you will get is this plus something.
Plus something.
I thought that was a constant.
And for every constant, if you take n large enough,
It goes smaller. Oh, okay. Okay. So then maybe I'm being a little sloppy with this.
but it says that it says that probabilistic method does not give you an answer.
Okay.
Yes, that it's the standard of this.
So maybe the smaller one is even not there. So maybe.
Also the problem. So a random irregular graph is not a.
Usually doing this is
No, it's not exactly 2 square root d minus 1 over d.
plus.
You will get some small amount of it. You need some slack, I presume. I somehow thought the definition here also has, maybe it does, but whatever. Okay. So it will sometimes be convenient to keep track of these parameters, like basically the number of vertices, how regular your graph is, and what your current spectral gap is.
So, sorry, one question here, just a little distract. So the existence of Ramanujan graphs was not proven by Alon Lubotsky Phillips, right? Or did they? Not
Lubotsky, Phillips, and Sarnak.
Lubotsky Phillips and Son. Was it? I mean, so.
Oh, you're saying prior to Lubotsky, Phillips, Sarnak, were there known existent results of?
Yeah, there was no, that I almost am sure. But
probably.
Even Lubotsky Phillips Sarnak, did they prove the existence of?
No, they gave a construction. They gave an explicit construction.
Only for prime power.
Yeah. So I will look at it. So
That's
for every degree and
Bipartite
Ramanujan graph for every degree.
I keep confusing.
Yeah. I'll mention the LPS graph. I'm not going to tell you what the graph is, but I'll mention what the parameter is. So, okay. So something that, because we'll be dealing with graphs and we'll want to keep track of these three parameters, we just use this notation that Salil uses in his manuscript, which is, I'll call something an ND gamma graph to mean that it's something on n vertices, it's D regular, and it has a spectral gap of gamma. Okay. And so what is the goal going to be? The goal is going to be, we have a particular target gamma that we have in mind. This is the spectral graph we want to achieve. Okay. And what I want to do is actually to build a family of graphs. I don't want to just build one graph. I want to build a family of graphs because that's how we are going to use it in our randomized to somehow do error reduction and so on. And this family of graph, let's say it's indexed by some I. So GI is some NI, DI, gamma I graph. And what do you want from this? I would like NI to keep increasing as I tends to infinity. We'll somehow quantify this a little further to sort of say that I also want NI to not be too sparse. It shouldn't be the case that, if you ask for a 100 vertex graph, I'll tell you that, look, I either have a graph of one vertex or I have a graph of a billion vertices. So you want to sort of say that the jump between NI and NI plus 1 is not too large. Okay, I'm not encoding that in the definition right now, but intuitively, let's just say that I want to build a family of graphs in the sense that the number of vertices goes to infinity, but I want the degree to be bounded. So, something I didn't write that. Okay, Oh, I did. Okay. So I'm basically saying that all of these are going to be D-regular graphs. Okay. I have a fixed parameter D and I want all of them to be D-regular because that's my budget. And I also want the case that you have a guarantee on the spectral gap. That is, all of these spectral gaps are at least as large as the target that you want. Okay. And these are the sort of constructions we are going to be looking for. Okay. And as mentioned earlier, there are two notions of explicitness in these things. The first notion is saying that if I ask you for the ith neighbor of a vertex, I'm going to use the notation gamma of v comma I to indicate this. Okay, I give you a vertex v and I give you a particular I between 1 and t, and I ask you tell me the ith neighbor of v. How much time are you going to take? And one thing could be that I want to take time proportional to the number of vertices in the graph. This is what you would do if my expectation is to basically write down the adjacency matrix. If I'm allowed to do that, then I can look at the ith row, and figure out what is the ith one that shows up there. Okay, so that's what I would have done in the weakly explicit case. But as we mentioned previously, that we'll often be dealing with graphs on exponentially many vertices. So we don't want to run in time like the poly in the number of vertices, because the number of vertices will often be very, very large. So what we want is a strongly explicit construction, which is to say that I give you a vertex v and an edge index, like the degree index I, and I want you to run in polynomial time in the input length. And what's the input length?
I is overloaded.
Okay. Yeah, so this should have been, let me call it J probably. Okay. Okay. And here I basically want to say that the input length is basically a vertex label and a degree label. A degree label is of course no more than the vertex label. And the label length is only logarithmic in the number of vertices. So I would hopefully like to run polynomial in that. So I want to run in polylog in it. So this is a strongly explicit situation where I'm not expected to write down the adjacency matrix, but you ask for a vertex, I have enough time to sort of list out the neighbors if you want. Okay, if d is small, I can just run over I j equal to 1, 2, 3 all the way till d and then give you that list. Okay, and this is what we are going to try and get. I want to get strongly explicit expander families. Good. So now let's look at some examples of expanders. So these are fairly well known and they've been well studied for a long time. But I should also mention that these are all expander families that are easy to describe, but hard to prove. Okay, all of this will fall under this category of I'll be able to tell you what exactly this graph is, but then you'll have to just take it on faith that these graphs do form expanders.
No, you mean like all of this would be strongly explicit?
They're all strongly explicit. They all satisfy all the properties that we would want. Almost all the properties that we would want. But it's just that you just have to take it on faith that these are expanders, or if you want to prove it, proving these usually involves some fairly large hammers. Okay, so one of the earliest constructions is by Margulis, which I will describe. And here the vertex set is basically pairs which are between 0 and m-1. So you could often think of it as z mod mz cross z mod mz. Basically, these are all pairs I comma j, so where I and j are both between 0 and m-1. So there are like m squared vertices in this graph. Okay, and these are the neighbors. So a pair x comma y is connected to the following 8 points. So you go one step forward in x, one step forward, one step back in x, one step up, one step down, and then you do some diagonal business, and then you something. There's some eight neighbors that you have. There is a reason for this being this 8. This is something to do with a certain group action on these set of vertices or something. And the theorem of Margulis basically says that there is a fixed constant gamma such that all of these are gamma. They have a spectral gap of gamma, no matter what choice of m you want to choose. Okay, and as you can see from the above, it's an 8 regular graph.
So this M need not be a prime or.
In this is one thing where M does not. So this is truly and strongly explicit graph, because obviously, if M, even if you set M to be like a very, very large thing, these computations of what my neighbors are like trivial. You just need to add one or subtract one, so some such thing like that. So these are truly strongly explicit expander graph constructions. They get some spectral gap. I don't know what this gamma is, but you get something. Okay, the proof of Margulies' theorem gives you one such.
This is quite controversial.
Yeah, I don't know what goes into the proof. All of these have I have seen what goes into the LPS proof. So usually there'll be statements of the form: you take a co-compact torsion-free subgroup of this group, and then something happens. So it uses some representation theory, and I think this one is actually not very hard to prove. This is a linear, Fourier linear vector set. Gaber-Galil actually gave an elementary proof of the Margulies construction. Yeah, and in fact, I think I've seen Margulies in two forms. There's a slightly different version of this graph, which is 9 regular. I don't know. I mean, like, so there are some graphs that work. Okay, so this is one example of an expander. Okay, so then there's this other graph, which is like one of the easiest to describe. And I don't think it's called the Selberg graph, but I'm going to call it the Selberg graph. So the set of vertices is basically just the residual mod P. And it's a 3 regular graph.
Now P is prime.
Here P is a prime. No? It's a 3 regular graph. And the neighbors of I are just the following. It's I plus 1, I minus 1, and I inverse. Now, obviously, 0 inverse doesn't make sense. So we'll just assign 0 inverse to be 0. Okay. So this is a 3 regular graph. And again, turns out that this has some spectral gap for all primes. Okay. And to prove that this has spectral gap, you use something called the Selberg 3/16 theorem, which is supposed to be a major theorem in number theory. And the proof of this fact uses that. That's why I was calling it the Selberg graph. Okay. And LPS, I'm not going to describe what the graph is, though it's not very hard. If you look at the previous pseudorandomness offering, there the description was there. But LPS usually has 2 parameters involved. You need to choose 2 numbers. One is a prime, which is P, and the other is a prime power, which is Q. And there are some expectations of what you want from Q. So this Q must have there must be a square root minus 1 inside mod Q. There must be some I such that I squared is minus 1 in Q. Okay. And this GPQ graph, which is the LPS graph with parameters P and Q. So the Q controls how many vertices you want. So the number of vertices is basically, you take FQ, but you add a point at infinity. So therefore there are Q plus 1 points. And the degree turns out to be P plus 1. But most importantly, the spectral gap that you have. Okay, let's think of it in terms of the eigenvalue. The eigenvalue lambda that you achieve is square root P over P plus 1. Notice that if D is the degree, then this is going to be 2 square root D minus 1 over D. And this is exactly what was the condition for the Ramanujan, to say that a graph was Ramanujan. No, I haven't described the graph. The graph is a little messy. Yeah, something to do with the Mobius sort of transformation of the group. It's not hard to describe, it's just writing it down is a pain. And I was not going to do anything besides show you this result, so I didn't want to. Okay, but the point I wanted to make is that the lambda here, so lambda of GPQ, this is actually equal to 2 square root of D minus 1 over D. And that makes this a Ramanujan graph family. Okay, so, and all of the above graphs are strongly explicit. And there is just a mild situation in the sense that, in the situation where you need to choose the number of vertices to be a prime, the non-explicit part of it is to figure out the prime of the right length and so on.
So here Q is a power.
Q is a power of a prime.
power of P being the prime? Or
No. So in fact, if it's, I think, okay, it should not be equal to P, but it can be anything that has a square root of -1.
So it doesn't have to be divisible by.
No, it doesn't have to be divisible.
So these are completely independent parameters. But
Yeah,
It
yeah.
has to be, the graph is like for
Wait, one second.
What?
Oh, sorry. No, I think Q must be a pth power.
Yeah.
Sorry, I messed up here. So this must be a pth power. And it can't be P.
The power of what?
Sorry,
Oh, some power of P. Q might be some power.
power of P, and it's not supposed to be P. It can be any other thing, but it must additionally satisfy the property that there is some I such that I squared plus 1. I'm maybe messing up there's some extra condition. Huh?
This P satisfies it, Q will automatically satisfy it.
P satisfies what?
That P has a square root of -1. Okay.
Yes. But this is not, as you said, this is not truly explicit because we still know how to generate large points.
Yeah. But I mean, the point I was trying to see was the P is going to capture your degree. So maybe you just choose a small prime. And if you're allowed to choose Q to be a large enough power so that it has a number of vertices, maybe it's okay. Yeah, I'm not exactly sure, but for most purposes, these graphs are already good in the sense that their graphs are growing number of vertices. It's not like the number of vertices are too far spread out. Like it actually grows at a decent rate. Okay, because there are always primes between n and 2n and stuff like that. Okay, and all of these, the neighborhood, getting a sense of the neighborhood is actually very, very efficient. You can do this in polylog of the number of vertices.
So could generate primes, large and large. Yeah. Then, no, this would, okay. No. Anyway, because you have to, because if you start making P tending to infinity, the P has to exponentially grow with the parameter of interest, right?
So typically, in our construction, we'll be dealing with, I want the P to be small because that's the degree. But I agree, in general, yeah.
In general, because then, of course,
then you will have to choose a prime that is in the right range. Yeah. And at the moment, we don't have deterministic algorithms for this.
No, but then the lambda will become like closer and closer to 1. So it will be like.
No, Akhile's point was, suppose you are okay, you actually want to build graphs where the degree itself is also growing too fast.
Okay.
Then in that situation, this is not really an explicit construction because it seems to involve finding a prime of the right magnitude. And we don't know how to do that. Okay. So what we are going to do in this class and the next class is to do what I'll call combinatorial constructions. This is like completely from scratch. Okay. And there are some advantages, but I mean, like, there are some concrete places where it's these constructions that give you the results that you want and not the fact that there do exist such graphs. Okay. But I do think that, but besides this, it's just a really, really elegant construction, and it's one of these very hands-on things. You can actually literally look at what is happening here, and you completely understand what is going on in these things. And they're very easy to analyze. Like we've set up the machinery so that the analysis will actually be quite simple. And the key advantage that this combinatorial construction has over the previous things is the fact that it allows you to sort of expanderize a graph. Like if you already have a certain connectivity structure, it gives you a mechanism in which each connected component will become more and more of an expander, but you don't change connectivity relations that you originally had. And this is going to be crucial when we want to eventually say that undirected graph connectivity is in log space. Okay. So those are some of the advantages of doing these combinatorial constructions, but it's just something that's actually very nice to work with. Okay. And the rough plan is basically the following. We'll start with a decent graph. Decent expander and improve. And we can be very loose about what we mean by a decent expander. You can start with a cycle. I mean, all I just want there to be some spectral gap. And we're going to come up with a series of operations that allow us to increase the number of variables, keep track of the degrees, improve your spectral gap, etc. And we eventually, our goal is to put all of this together to build the family of graphs that we want. Okay, so that's going to be the thing. And whenever we are dealing with these graphs, it's always good, because whenever we are talking about what does it mean to say you compute the adjacency relation or something, it's often actually better to work with what are called rotation maps. Okay, let me just describe what a rotation map is. It's just one extra thing based on the standard adjacency relation. Normally, I give you a vertex and I give you an eye, and I ask you, tell me your ith neighbor. That's what I would have normally asked. So the input is still something like that. It's given a vertex and it's given an eye. But what I'm asking it to output is not just a vertex. I want it to output a vertex and another edge index or a degree index. And intuitively, the expectation is what I want is the following. I want to say, if I feed this u comma I, I want it to return v comma j with the following guarantee, where the intuition, roughly this is what it's supposed to be. I want to say v is the ith neighbor of u, and u happens to be the jth neighbor of v. Okay, so that's what the rotation map sort of gives. And
so here we are assuming locally
each vertex is going to label its edges. This is my first neighbor, second neighbor, etc. I'm expecting no consistency across vertices. Okay, and Jayakumar calls this the J part of it as a hum aapke hai kaun sort of a thing. It's like, what am I in your relations thing. And notice that it's set up in such a way that if you apply the rotation map twice, you get back to the same starting. Because I mean, it's an involution. Right? So whenever we are building these graphs, we'll often get a sense of what is the rotation map for this graph. Or you modify a graph, I want to know what is the rotation graph map of the modified graph. So this is what we'll be dealing with often. And it's going to be very useful when we eventually analyze stuff. Okay, now let's look at these graph operations. We are basically going to consider three graph operations. Okay, there's one more that I'll mention but not really analyze. But roughly speaking, the three graph operations have the following features. One of these graph operations will improve your spectral gap. One of these graph operations will increase the number of vertices. And one of the graph operations will reduce the degree. So there's one for each of those things. We just need to put them together in such a way. Obviously, when we improve one, we might end up messing up one of the other parameters. We just have to do it in the right structure so that, at the end of it, we still get some target expansion. So the simplest to describe is this notion called the powering operation. Okay, so given a ND gamma graph, I'm going to define a new graph G squared. I really shouldn't be calling them graphs. I should be calling them as the random walks. Because the graph sort of, okay, here when I mean graph, it's going to be there are multiple edges possible and so on. I'm totally okay there being multiple edges between two things. Okay, so I want to define the graph G squared. And intuitively, this is like running two steps on. That is, you take one step and then you take one. Every step on the graph G squared corresponds to taking two steps in the original graph G. Okay, and let me just write down what this is. So this is going to be a graph on again n vertices, but the degree is going to become d squared. And we are going to get some new spectral gap, which we'll analyze shortly, like what that will be. Okay, and so what is the adjacency relation going to look like? I give it a vertex u, and suppose my edges now look like I1 comma I2, because the degree is now going to be d squared, which I'll think of as a two tuple of d and d. It's just convenient to think of it this way.
U is what is U?
So u is an element of this is an element of n, and both of I1 and I2 are elements of d. So I want to know what is the I1, I2th neighbor of u in the graph G squared. Okay, and what is that going to be? You do the most obvious thing. You look at the I1th neighbor of u. Okay, and then take the I2th neighbor of this guy. whatever was this new vertex.
That's like this.
That's like taking two steps, right? I mean, you take one step according to I1, you look at the I1 at the edge, and then you take the I2 at the edge. So it's possible that you return, you come back to the same vertex. This graph may have self loops, we don't care. Okay, and if you think about it in terms of rotation maps, this is, if you were to write this as code, this is what you would have written. I want to find the rotation map of U with respect to I1 and 2. I first compute the rotation map of U with I1. I get U1 and J1.
This first one is.
Okay, then I compute U1's rotation map with I2. So I get some U2 and J2. So U2 is where I should land up. But I also need to know, if I were to retrace my path, what should I do? So I should first take the J2th edge and then the J1. So you just need to be a little bit careful when you're writing this, but there's nothing fancy going on. Okay, I hope the powering operation is sort of clear. And so the natural thing to ask is what happens to the spectral time? Okay. And in fact, there's one of these things where you can actually get a sense of. So if you look at the adjacency matrix of G squared, what is this in terms of the adjacency matrix of G? It's called powering because this is actually equal to just you take the adjacency matrix of G and then square.
In an adjacency matrix, how do you encode this information of ith neighbor of U?
Oh no, okay, I'm not okay. Yeah, that's a good point. Yeah, that's true. I mean, I'm just going to, if there are multiple edges, I'm going to put multiple things.
Yeah.
And now each vertex decides amongst the different entries that it sees in that row. I mean, counted with multiplicity. It just calls them, this is my first vertex, second vertex, etc.
But in the analysis of the expansion.
So we don't particularly care about the labeling of those.
That's right.
Yeah.
All that matters is the connectivity.
That's right. That's right.
But somehow to describe this graph, this thing becomes.
Yeah, it becomes more convenient, and I'm writing it this way because eventually I want to say that if the graph G was explicit, then the graph G squared is also explicit because I'm doing very few operations on G.
You can add in formal variables.
Huh?
Ij in the adjacency matrix.
Yeah.
If there is a non-zero entry, then so let's take like D square variables x of ij, I in D. J
Oh, yeah, on every entry you just add which some sort of indicator to sort of say this is
and then I think it does preserve. You can actually read.
Yeah, so then the number of columns and the number of rows will increase, right?
No. So each entry, instead of just putting a 1, he's saying if this is the first neighbor, you put XU1 or something.
Yeah.
It doesn't mean a Boolean matrix, but
Yeah, it's a symbolic matrix.
It's a symbolic matrix.
But it will actually, I think this will like you will be able to read out your.
Yeah. Okay.
See, also the rows or columns are ordered in one way, and
Yeah, you could just order them in one way and then. So it's very easy to sort of see that, basically the random walk matrix or the adjacency matrix is literally just the power of whatever you started off with. Okay. So obviously, what is going to happen to eigenvalues? So then this implies that, if V was an eigenvector for AG, okay, I shouldn't be writing A probably, I should be writing the random walk matrix. I mean, basically they're all the same. They're going to get scaled appropriately. So if I take a particular eigenvector for mg squared, we know that this is MMV. So the first application of M is going to give me like a lambda. And again, I'm going to end up with the same vector. So basically, this is going to end up being lambda squared times V. So the eigenvalues of the square of the matrix is nothing but the squares of the original eigenvalues. Right? So this implies that lambda of G squared, this is basically going to be lambda of G, the whole square. Because the 1 is of course going to stay at 1. But then I'm told that, amongst the remaining thing, which is the one that has the largest absolute value. Well, the largest absolute value, now whatever the old one was, it now gets 2. So if you think about this, what is happening here is like taking a powering. I mean, I define squaring, but you can do the same thing for some power k. What happens in the process is your lambda sort of starts dropping. So your lambda becomes smaller and smaller. So you're improving your spectral gap in the process.
At the cost of degree.
Yeah, but So the number of vertices is staying the same. Unfortunately, the degree is becoming much worse because the larger power I take, the degree becomes larger and larger. But the gamma is getting better. Either lambda is getting smaller or gamma is getting larger, whichever way it's getting better. So we are improving on one of the parameters, but at the cost of degree. Okay. So this is operation 1. It's very simple to describe operation. Hope things are clear. Okay. So the next operation is something called tensoring. Okay, where you are given two graphs, G and H, and the tensor is sort of defined as it's something where you combine G and H together in some way. Okay, so let's say that G is a graph, some N1 D1 gamma 1 graph, and H is the N2 D2 gamma 2 graph. Now I want to know what does this tensoring mean, and intuitively speaking, you should be thinking of the vertex set for the tensor product as made up of pairs of vertices, one from G and one from H. And a walk in the tensor product graph is like you're taking a parallel walk on G and H respectively. Okay, so written it. So the degree is going to be D1, D2, and the I1, I2th neighbor, where I need to be specific about this I1. So this I1 is something in D1. This I2 is something in D2. This U is something in N1, and this V is something in N2. Okay. Maybe, I don't know why I wrote V1 here. This is supposed to be, let's call this U2. Okay. And what are you doing? You're basically, the new pair that you land up in is the I1th neighbor of U1, comma, I2th neighbor of U2. It's like as if you took a parallel step in both of these.
Right? Because tau G U1 I1 would give you
again something in N1.
No, I know, but it will be like because you want the things to be ordered in the
So this should have been
the projection of that on the first. Tau G1
So this should be H. Yeah.
No, not just that, right? Because you're trying to arrange this thing as U1, U2, it should give you back as
Oh, sorry. No, right now I was just writing gamma, which is the neighborhood relation, not the rotation map. Yeah, but I'll soon just give the code for the rotation map code is just this.
Oh, I see.
Okay, so you again you look at the rotation map of G. Again, I seem to have missed G and H. So this should have been H. You do the rotation map of H, and then you just plug in J1, J2 as the other. Okay, so let's look at some example. Okay, just to get a sense of what does this graph now look like. So suppose my graph G was this, and my graph H was this. So the new graph sort of it's made up. You should think of it as like each of these vertices of G sort of get replaced by a copy of H. Okay, so I want to think of this as okay, and now I need to give a sense of how do you connect stuff together, and how are you going to connect them together? You basically this corresponded to an edge here. So you connect all vertices here to all vertices. I mean, in the sense that connect them across clouds if the corresponding parties were connected. So for example, there will now be an edge from this to this.
You don't have the original triangle edges.
I don't have the original triangle edges. Basically, what you do is you just put edges. I mean, if A and B were connected inside H, but this was cloud U and this was cloud V, then A in cloud U is connected to B in cloud V. So there is some, so therefore there's some bunch of edges that go like this.
But DCS won't be present. DCS won't be present.
Sorry?
This original triangle.
Yeah, the original triangle won't be present. All the edges are basically things in the green part. I mean, like across clouds in some sense. The only time a triangle, things inside that might be present is if the graph G happens to have a self loop. Then that might induce edges within the cloud. Otherwise, they're all only what are inter-cloud edges. Okay.
But somehow this is not a community operation.
It is.
No, it is, right?
Then
Then
the self loop, why should it only matter in the graph? If G had something, you should be able to express it as.
No, if you're expressing it as clouds of G, then.
Right.
Yeah, so I mean, you could also think of it as like every vertex of S is split into a square, and then there's some connection between them. It's just how we order the vertices. Okay. So the next thing you might want to get a sense of is, okay, fine. We now know what the degree is. We now know what the number of variables is. I want to know what is the spectral gap. Okay. And there are many ways to see this, and it's always instructive to just look at the adjacency matrix and ask, what is this new adjacency matrix? Okay. So in this case, the adjacency matrix of AG was what? It was something like 1 0 1 0 0 1 0 1 1 0 1 0 0 1 0 1. Okay, and the matrix of AH was, I think, 0 1 1 1 0 1 1 1 0.
It's not diagonal 0.
Oh, I maybe swapped. So this is what it should have looked like. Okay. Now, what is going to happen to the tensor product of this thing? So let's try to write down this matrix, but we will try to write down this matrix into convenient groups. Okay. So I'm going to think of this as like a 4x4 blocks. Okay. Where these are all vertices in the cloud corresponding to vertex 1 of G. So there are three things here. And these are things correspond to vertex 2 of G, and so on. Now, obviously, if vertex 1 of G was not connected to vertex 1 of G, there can be no edges between something in vertex 1 of the cloud of that to itself. So if something used to be 0, it will just be a big block of zeros. Right? So this is just a big block of zeros, this is a big block of zeros, and so on. On the other hand, if it so happened that vertex 1 was connected to vertex 2 in G, now I need to know within the connections between cloud of U and cloud of V, what all am I supposed to put? Well, I'm supposed to put the connections according to whichever were connected as per H. So therefore, what is supposed to go here is actually AH. Yeah. So in general, if there are multiple edges there, then that number will sort of stick as a scalar multiple of this edge. And this is truly what is called the tensor product of two matrices. If you take a tensor product of two matrices, you literally take the second matrix and blow them up into blocks within the first matrix. So, and this is just AG tensor AH. Again, I'm assuming that you're labeled the rows and columns correctly. Okay. So natural thing to ask is, okay, now you know what the matrix is. So again, the random walk matrix will also be the tensor product of the corresponding random walks. So you want to get a sense of, what do the eigenvalues look like? Okay. And here is a very simple fact. It's not hard to prove. Now, just like you have a tensor product of matrices, you can also take tensor product of vectors. You take a vector v1 and another vector u, vector v, and just replace every entry by the other vector. Now I want to know if I take A tensor B and act it on U tensor V, I'm assuming that the dimensions are correct. That is, A correctly acts on U and B is something that acts on V. I want to know what happens to this action. And intuitively speaking, it's like U tensor V is like saying U is something that happens on graph G and V is something that happens on graph H. And the whole point of a tensor product was doing a parallel situation. So you sort of want to say that this ought to be AU tensor. Okay. So a particular corollary is that if U happens to be an eigenvector of A and V happens to be an eigenvector of B, then U tensor V is an eigenvector of A tensor B and the eigenvalues will just multiply. Okay. So let's just see a proof of this. I'm just going to give a proof by example. So, okay, so I'm going to sort of think of this matrix as 4 things. So this is A11, A11B.
So both the operations
A1 to
that
B
is described so far, the degree does.
The degree is increasing. Okay, so in general, this is I don't know A.
But here the number of vertices are also gone up,
Yeah, here the number of vertices has gone up. That seems like a good thing.
and the eigen and the.
We'll see what happens to the eigenvalues soon.
Well, they multiply, right?
Yeah, but okay, we'll come back to that. So this is U1 times V. This V is a vector though, and then UN times V. So if you were to take this product, what is going to happen? Okay, so let's just focus on what is the first block going to. And you just notice that what you're going to end up getting is A11 U1 plus blah 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 till A1 M UM. This scaled with BB. Okay, and in general, there will be the mth thing again scaled by BB. But this is the same thing as you take the matrix A applied on U, and then you take the tensor product with the matrix, with the vector. You just need to write down what you get and then notice that this is exactly what happens. Okay, and if AU is equal to lambda U, lambda 1 U, and BB is equal to lambda 1 B, lambda 2 B, then A tensor B of U tensor B, this is just going to be lambda 1 lambda 2 of U tensor B. So you now get that all the eigenvalues sort of become perfect. Okay, now comes to the thing. What is the spectral gap then? So the eigenvalues of G tensor H are all possible products, like pairwise products that you could get by taking an eigenvalue of G and an eigenvalue of H. The one eigenvalue is one that you get by taking the one in this and one in this. I want to know what is the next highest you could possibly get. So there are actually 2 choices. Either it could be 1 multiplied with lambda 2 of the lambda of H part, or it could be the lambda of G multiplied by 1. Now I don't know which of the 2 is larger. Okay, but certainly this is like at most in fact this is exactly equal to the max of lambda of G and lambda of H. So the spectral gap therefore is going to be the min of gamma, what did I call it? Gamma 1 and 2? Yeah, I was calling it gamma 1 and 2. I'll just write gamma of G and gamma of H. So then gamma of G and gamma of H. Okay, was this clear so far? As to what's happening to the spectral gap? Good. So if you think about it in terms of parameters, the number of vertices went from n to n1, if the old number of vertices was n, and if I managed to take a tensor product with something involving n2 or n times, so if it was n1, it went from n1 to n1 n2. That's sort of what happened. The number of vertices went up. Now it's a graph on more number of vertices. The degree, unfortunately, also went up. Okay, it got multiplied by whatever was the degree of the thing you took a tensor product with. And in gamma, it didn't worsen. That is, whatever was the worst of the expanders between the 2 graphs you took, well, this has at least as much expansion as the worst expander between the 2 things that you took. So it didn't become bad, but it's not like it improved. So at the moment, if all I had with me was tensoring and powering, the problem with both of these situations is that the degree is going up all the time. And we need one mechanism in which we bring the degree down. And hopefully, and we understand that this has to happen in some way, because powering is sort of letting you make lambda as small as possible. We know there is some inherent tension between lambda and the degree. So obviously, if you are allowed to make lambda as small as possible, your degree will shoot up a bit. But right now, it seems to shoot up a lot. We have no way of controlling it. We need some mechanism to control it. And that's where the third operation is going to come. Okay, so like I mentioned, all the above parameters make D worse, and therefore we need some operation to fix it. Okay, so the ideal situation is going to be the following. I start with a graph ND gamma 1, which I should think of as saying this is graph that has the right number of vertices in my opinion. Like I managed to increase N to the target that I would like. I managed to push gamma, like the spectral gap, as high as possible. Like I needed a spectral gap of at least some the target gamma. I managed to push that. The problem right now is that the degree is also large. So I want to somehow bring the degree down. So what I want to do is I want to take a small graph, a graph H, which is on small n vertices, small d degree, and maybe it has some spectral gap gamma 2. Okay, some base graph that I want to start off with, and somehow do some operation, which I was just at the moment writing G star H. I don't know what I have to do. But the intention should be the following. It must have roughly the, like if I zoom out and look at this graph, it should sort of look like G in the sense that it has a lot of vertices. It has as many vertices as G does. But somehow the degree of this graph is something which is a function of small d and not capital D. The connectivity structure is somehow determined by what H is telling you locally. But when I zoom out, it sort of looks like the original graph. This is what I would like it to be. Okay, then I can hope that, then we can hope that, okay, in the process of doing this, maybe the gamma didn't become like much worse. And we'll analyze that independently. But I just want to get this sense in mind that you want to combine the graphs G and H such that this new graph has like basically as many vertices as G does, because I don't want to lose that. But I want the degree to be like some function of H. I don't want the degree to be a function of G. Okay, is this okay so far? And one of the simplest versions of this is what is called the replacement product. But this is not what we will analyze. Okay, because it's actually harder to analyze. So we'll analyze a different product. Yeah, that also we would want. But let's first try now with some construction and then hope that we can then analyze the spectral gap. So the replacement product will satisfy the above construction, but analyzing the spectral gap is a little bit of a pain. Okay, so let me define what the replacement product is. Here, you need to tailor the parameters correctly. So the big graph is a graph on n vertices, degree capital D, and some gamma 1. But I want the smaller graph to be something which is on d vertices, maybe much smaller degree, small d, and gamma 2. Okay, and let me try to draw this graph pictorially to sort of see what happens. So let's pick up a vertex U of G. I mean, there are some D edges going out. Okay, that was what the graph G looked like. I now need to tell you what happens in the replacement product. So the replacement product sort of looks like this. So you erase off these things. Okay, and you put one vertex in place of all the edges in the cloud of U, and you connect them according to H. So what is sort of happening is that every vertex of G is getting replaced by a copy of H. And it's like as if every vertex of H is now sitting on an edge. So if I had if for example, if this vertex was getting connected to whatever V, now this V cloud will also have a copy of H sitting inside. And one of those vertices is this vertex. So there is a blue vertex here, and there's a blue vertex here. So every edge of your original graph G is now like connected between two H vertices on two different clouds.
H vertices meaning two H vertices.
Yeah, so this is like one cloud, this is like the other cloud. And like we've replaced every vertex of G by a cloud of H. And now the connections are between, it's like as if in my cloud, every vertex is responsible for one edge. So it's sitting on those spokes. Okay, and this is what is called the replacement product. Okay, what can I say about the replacement product? It's now a graph on ND vertices because every vertex of the original graph G is replaced by a copy of H. but the degree is now d plus 1. Because every vertex has the connections inside the cloud. There are d connections. Oh, sorry. So I have d connections here. Plus one edge going out. So the new degree is now small d plus 1. And in some sense, if you zoom out a lot, it somehow feels like it still looks like a copy of G. There is something happening inside every original G vertex. There's a whole bunch of mess happening there. But that mess looks like H. And somehow this seems to have the flavor that, oh, okay, so it looks like not just connectivity is preserved. Roughly speaking, mixing may also get preserved somehow. We'll have to analyze this, but it's going to be a little bit of a pain to analyze. And it so turns out that gamma, of course, will worsen, but it doesn't worsen by a lot.
Gamma 2 is still good, right?
Yeah, but now it will be like, it will be worse than gamma 1 and gamma 2 in some sense.
Right.
But hopefully you have gained on the gamma so much that this amount of loss you can handle at this point.
You have gained on degree, not gamma.
Sorry?
You have gained on degree, not
No, in the sense that previously, if I imagine doing this thing, or I do a whole bunch of powering operations, so my gamma really became very close to 1. And now I did this one replacement product, it becomes smaller. But now it's like, I still have a decent gamma and my degree is now manageable. Hopefully.
The point is, I guess you H as a good expander
on a small number of vertices
with low degree.
Yeah.
And G is a good expander with a large number of vertices.
Like G is a really good expander on a large number of vertices, except the degree is little bit.
Now you're
somehow trying to mix the two. Okay. So this is what is called the replacement product, and it turns like more painful to analyze. So what we'll instead analyze is something called the zig-zag product. And it's a really beautiful construction. And I'll give you two different perspectives of the zig-zag product. I don't think we'll have time to analyze that in today's lecture, but we'll do that in the next class, and it'll be surprisingly simple to analyze. Okay, it's almost like it's set up to make sure that the analysis is actually easy. Okay, so let me define what the zig-zag product is. So the situation is sort of very similar to the replacement product in the sense that the degree of the large graph matches the number of vertices of the small graph. Okay, so that's the situation that we are in. So just like we have in the replacement product, the first step in this is to take your graph G and replace every vertex of your graph G by a cloud. Okay, so here is what I'm going to do. So maybe I had a vertex U. Let me draw this U. Let me write it here. And this was connected to vertex B. And this black edge, this is something in G. Okay. And whenever I'm drawing a red edge, that will be something in H. So that we do this. And what is going to happen, just like the replacement product, this U is going to get replaced by a cloud. And V is going to get replaced by a cloud. So there are a bunch of vertices sitting here. Okay, so maybe I should have done this a little better. Sorry. Okay, so there is one red vertex that was sitting on this edge. Maybe there are other red vertices. These are all vertices of H that were inside that cloud, and similarly, so similarly, there are vertices of H that are sitting here. Okay. Now, once I fix the particular edge UV, there is a particular intercloud edge that I care about, which is connecting something in cloud A, cloud U. Let me call this vertex as A. And here it connects it to B. A and B are vertices inside the graph H. Okay. Now, maybe this A is connected to, I don't know, these two vertices. And let's say the graph H was, I didn't even put the same number of things. Let's say the graph H was a hexagon, like just a 6 cycle or something. So this vertex A is connected to these two vertices and B is connected to these two vertices.
Those are now you just drawn red, so those are just copies of H.
Copies of H. Okay. And what I'm going to do now is the zigzag product edges. I'm going to basically connect. Let me just say connect gamma H of A in the cloud U to gamma H of B in cloud B. That is, and basically these are the relevant neighbors of A. These were the neighbors of B. And there's going to be 4 edges like this. Those are my zigzag edges.
Those are that's like a complete graph, right?
So I put the complete bipartite graph on the neighborhood of the A vertex in the cloud U and the neighborhood of the B vertex in cloud B. Okay. So you basically think of the old replacement product itself, the way we were considering it. And the replacement product, this, I was looking at this edge UV. I want to know every edge UV is going to induce some d squared new edges. What are those new edges? Look at the neighborhood of this vertex inside this cloud. Look at the neighborhood of this vertex inside this cloud. Connect everything. Connect all of these D things to all of those D things. Okay. It's a slightly weird definition, but we'll soon see one more perspective from the perspective of rotation maps. So that maybe that might give a slightly different view of how to get this. But let's get a sense of how many edges does this new graph have? And by edges, I mean number of blue edges. The zigzag product is only made up of the blue edges. There are no red edges, there are no black edges. It's only made up of these blue edges. Okay, so how many edges do we have? So previously, maybe I had ND by 2 edges in the graph G. Now every edge is now going to get replaced by d squared edges. Because once I choose this edge, I am adding a whole bunch of d squared blue edges that are there. I should have made it like these are all the edges that I am adding. Okay, so therefore this is going to be this times small d squared. So this implies that the new degree
so this is
basically
like,
equal to d squared.
this is like we first do the replacement product and then boost it by the zigzagging thing, no?
So the edges in the replacement product are completely been removed now.
Why?
Because like edges in the replacement product involve these edges also.
Oh, those are gone.
They are all gone. The graph now consists only of these blue edges.
I see. And the black edges?
No black edges, nothing. There's only blue edges. Like
so you take
the black edge now there is not even any space for the black edge because.
So you take the replacement product, add these blue edges, that is guided by that, and then take off the red and black edges.
Exactly. You only have the blue edges in your graph. So it's a slightly messy operation, but we will see that it's set up to make sure that your degree is a function of small d. And I'll give you a slightly different perspective. Now I just wanted to convince you that even though I've done this thing of per each edge, I put a complete bipartite graph. Yeah. I just want to say that every edge is now replaced by d squared edges. But of course, the number of vertices is also increased by a factor of d. So therefore, the new degree, if you count correctly, will actually turn out to just be small d squared. Because the new number of vertices is capital N, capital D. So that ND thing cancels off and then you get.
Sorry, what did you say?
No. So the number of edges is supposed to be the new number of vertices,
which is ND.
Okay. Into the new degree.
Divided by 2.
Yeah, by 2. And we know that this is ND. And therefore the degree is going to be like this. As mentioned, it feels like why the hell is this graph regular? But you can think about it and then notice that it's actually a small d squared regular graph. If your G and H are regular, this will continue to be regular.
Basically, it's easier to just count directly. If you start from one vertex, you will take one step in the small.
So that's what I wanted to do now. So it's sometimes convenient to think of now what are my new vertices of this graph? It's made up of a pair U, A, where A is something in H I can either think of A as a vertex in H, or I can think of A as an edge label when it comes to the neighbors of U. There are two slightly different perspectives that we have, and I want to know what is this connected to. Okay, so let's say this is the cloud of U. So this is CU, and one of these red vertices is this A. Okay, good. So now this is maybe connected to some bunch of things. Okay, so I want to know what is this guy connect. This U comma A is what I'm referring to as this particular vertex, the copy of A inside the cloud. So what am I connected to? So suppose I ask you to go to a I1, I2th neighbor, or rather, what is the I1, I2th neighbor?
I1, I2.
So that is, I know that the new degree is like D squared, and I'm thinking of D squared as a pair, I1 and I2.
Oh, I thought you were trying to get also in the proof. This argument, make it clear why the new degree, why is it a regular D square regular?
Yeah, I'm going to tell you what the I1, I2 neighbor of U comma A is, and I'm going to tell you how to compute it. That will tell you that, okay, these are my D squared neighbors. Okay, so now what I'm first going to do is I start from vertex A and ask, what is my I1th neighbor? Okay,
Oh,
so the vertex A is I1th neighbor, maybe is this new vertex A prime. Okay, now A prime is sitting on a certain black edge. That is going to end up reaching to probably a different cloud, CV. And maybe I end up in some vertex here, which is over, let me call this vertex as B. And now I ask, what is B's I2th neighbor? That is maybe some other vertex C. Let me call, I don't know. Okay, let me C, I'm sure we confuse this. Let me call this B prime. Okay, and I'm going to just say the I1 is I2th neighbor of U comma A is actually V comma B prime. So the black edge is actually going like this. Oh. Sorry, the blue edges are going. So in some sense, what we are sort of saying is that you take one red edge followed by a black edge, followed by another red edge, and this corresponds to one blue edge.
this is the reason why it's called the zigzag.
So this is called the zigzag because it looks like you're taking a zigzag sort of. So okay, so there are multiple ways of looking at the same thing, but I hope this is sort of clear. So now I mentioned it in the like as if it was code. Like I sort of say I ask you for the I1, I2 as the neighbor. I'm telling you what you need to do. Now you can notice that if you keep track of the rotation maps in each of the steps, you will actually be able to trace back also. So building the rotation map of it is actually not hard. Okay. So what Reingold, Vadan, and Wigderson showed was this beautiful. So by the way, the zigzag construction is by Reingold, Vadan, and Wigderson, and they proved in their paper. I think they prove a worse bound, but we will see the following bound, or maybe their bound is better, but we will see this, which is much easier to prove, and hopefully it's intuitive. Like if one were to ask you, I should have probably done this. If I were to ask you to guess what the new spectral gap would be, it somehow feels like every edge in this walk, every edge in the zigzag product looks like two copies of H followed by one copy of G. Okay, and we will sort of see that the spectral gap actually is at least as large as this. It's gamma of G times gamma of H squared.
So why is it two copies of H followed by a copy of G?
Yeah, so the some so it's a little sloppy here, but at least it looks like an edge corresponds to two red edges and a black edge. Okay, and therefore it somehow feels like there probably like the spectral gap of G will hopefully show up twice, and the spectral gap of H shows up once or something, we need to of course prove all of this. Sorry, spectral gap of H shows up twice and spectral gap of G shows up once, and it turns out that this is what we will end up getting. Okay, so so basically this is the code for the rotation. If people are sort of interested, I mean, in the sense that if this helps you think about how to. So you first take a step in the graph H. Okay, so it tells you that, oh, you have to move to the vertex B1. So maybe I messed up what I was calling those and this. When I upload the notes, I'll correct them so that you have there's a similar mapping that happens here. But once you reach this new vertex, the edge in G that you are supposed to take is completely determined. There is no choice that you have in what G edge you are taking. That's the reason why this is the degree of this new thing is independent of capital D. Okay, so you take the edge that that vertex is supposed to be responsible to. So you move to a different cloud. And in that other cloud, you take the other step. The second step is actually just to make sure that the graph is sort of undirected and so on, to make it look symmetric. I think the same thing would work even if you just took one step, but then you you made the graph undirected, but this is just easier to analyze. So in the sense that if I just said you take one intra-cloud edge followed by an inter-cloud edge, it doesn't look symmetric, right? So by adding another intra-cloud edge at the end, you somehow forced it to be symmetric. I would suspect that if you just did intra-cloud followed by inter-cloud and just make the graph undirected by doing the same thing in the other direction, just adding the other thing also, I would assume that you will get a decent spectral gap as well. But this will actually turn out to be fairly easy to analyze. And that's what we will do in the next class. But I just say, I mean, this is all, zigzag is something that it always feels a little confusing because the graph description is feels convoluted. Okay, but it's good to get some intuition as to why did they construct this sort of a graph. So here is a thought experiment that I think you should.
Just one question.
Yeah.
Historically, before this RBW, there were also other efforts to, or is it like it didn't come out of the blue, right?
No, I would think that the replacement product was probably studied before.
Rosen and Madan.
Rosen and Madan actually were studying the replacement product.
This kind of techniques for constructing standards and constructing codes, people have been trying with applying like a sequence of operations. I don't know how to motivate this.
Yeah, so through the code construction or like.
So what happened with those constructions?
No, they also gave this thing. It's just that the way the replacement product works is that, I mean, the graph is too influenced by edge. Because if you are at a vertex, most of your edges going out stay inside the same cloud, except one edge that is going out. Right? In your replacement product, your degree is d plus 1.
Yes.
But the chance of you leaving the cloud is just 1 over d plus
1. Right.
So it's too influenced by what edge is.
I see.
So in the sense that the spectral
inherit the good problem.
You lose out a lot more on G, but you will probably be closer to H there. That might still be okay in this.
The H was good.
But I think that does give a pretty nice concept. This one is like somehow far easier to analyze. And so here is what I would like to thought experiment for you people to think about. So basically, I just want to end the class. The analysis is what we will do in the next class, but here is a thought experiment. Suppose the graph H that we are taking a zigzag with, this happens to be that is, it is on D vertices, has degree D, and spectral gap 1.
Sorry, one more. Is this zigzag product commutative? No, right?
No, because it actually the other one. Yeah. Okay. So suppose the graph H was the best graph you could hope for. It's the complete graph with self loops. It's like basically the all ones matrix is the adjacency matrix. So the spectral gap is like 1. It's the best thing you could hope for. Okay. You should just get a sense of what is G zigzag edge now?
D power D.
Okay, so we'll sort of see it.
D times.
Okay, I'm not going to tell what the thing is. I think this is something that if you work out, you will then notice that, aha, okay, so that's what, that's probably one reason why they considered this example, in the sense that if you take H to be the complete graph, then somehow G becomes a very, I mean, this becomes something that you have seen. This G zigzag with the complete graph becomes something that you actually have encountered before. Okay. And once you do that, then it will become, okay, so then you will know what the spectral gap is going to scale there. And in fact, this is how the proof is going to go. The way the proof will go is the following. We want to study G zigzag H. We are going to write H as gamma 2 times the complete graph plus 1 minus gamma 2 times some error. And we'll basically say, okay, now there will be two parts that will split up. And we will say, oh, the complete graph part, I know what it is. It's basically, you will intuitively have to tell yourself, oh, it's basically like. And then there is the other part. So somehow the proof will just follow from this in a very, very simple way. Okay. So to get a sense of things, unfortunately, I was trying to yesterday try to draw small graphs where I can draw the zigzag product, but it was totally not illustrative. So which is why I eventually didn't. But this, I think, is a great exercise. In fact, the way Salil does in his notes is that the proof for the tensor product, which just says that the eigenvectors are like the tensors of the eigenvectors, rather than proving it that way, he proves it via the mixing thing. He takes a vector V that is orthogonal to the all ones vector and literally shows that the norm of that drops. And that's a very nice sort of warm-up exercise to what we will end up doing here. Okay, so just to foreshadow what is going to happen in the analysis of the zigzag product, all that's going to happen is we will try to express this as a large matrix made up of something involving H followed by something involving G followed by something involving H. Because intuitively the graphs, every edge here looks like there's a red edge, black edge, red edge. But obviously you need to tie them up correctly. So we'll write that as a proper matrix product. And then we will make use of the matrix decomposition theorem. And this matrix product will split as one main term and one error term. And we'll be able to just analyze both of them fairly easily. And that's what will give us the analysis of the zigzag product. After that, I just need to tell you that with these three pieces, you can put them together to build your expander families. Okay, and we will see that. So that is going to be the rough agenda for the next lecture. Okay, so we'll stop here. By the way, I just want to remind that Tuesday, I think, is a holiday because of Ganapati Chaturthi, Vinayak Chaturthi. So we won't have a class on Tuesday. So the next meeting will actually be on Thursday, which is 1 week from now. And I also, in the meantime, try to come up with some problem set sort of a thing, and I'm supposed to correct the problem set questions. Okay, so I'll stop now and we'll meet 1 week.